So I want to start out today by taking us back to Friday. And in Friday's class, what we looked at was just the overall concept of separating out electrons into the two groups. The inner electrons, the ones that don't bond, and the outer electrons, the ones that do. The inner electrons we call core electrons. The outer electrons we call valence electrons. And some of the work that we did on Friday mainly just focused on how do I separate those two from each other, and how do I identify how many valence electrons there are. And the main answer to that question was the periodic table. The periodic table tells us how many valence electrons we have, and the octet rule tells us how many electrons we're shooting for. So the whole purpose of bonding, according to the octet rule, is for an atom to get to 8 valence electrons. And so what we're going to start with today is just a way of tracking the number of valence electrons that we have and beginning to try to frame that number of valence electrons in terms of what kinds of things it needs to do to meet the octet rule. So we're going to use a pretty standard model here for doing this tracking. It's called a Lewis dot structure. And Lewis dot structures are great because they give us a very simple way of looking at how many valence electrons there are. And from that standpoint, how many electrons are needed to get to the octet rule, and what kinds of methods are available for us to do that. Now, some general rules about Lewis dots. In a Lewis dot structure, what we're going to see is that we're going to have our elemental symbol in the middle. And it's going to be surrounded by the dots. Now, the dots themselves are going to show up in 4 different areas: above, below, and to either side of that symbol. And we want to think about these zones kind of in the same way that we do orbitals. So I got a couple of questions from you over the weekend about Hund's rule. Remembering why don't I just pair up my electrons in the first orbital? Why do I separate them from each other? And the simplest answer I have for that has to do with the concept of repulsion. Electrons have the same charge. Like charges repel. And so the question becomes, why does Hund's rule exist? Well, Hund's rule exists primarily so that we can separate those electrons from each other so that they don't have to repel each other as much. So if I've got 3 orbitals to put electrons in, I'm going to put them in 1 orbital at a time until I have to start doubling them up so that they don't have to repel each other as much. That's the basic idea for why Hund's rule exists. We're going to apply similar logic to these 4 zones around the atomic symbol. So when we're drawing up dots, we're going to put dots in those 4 areas, above, below, to either side, until we get to the position where we have to double them up with each other. So in terms of the rules for these dots, the number of dots in my structure is equal to the number of valence electrons that I'm supposed to get. So I look at the periodic table tells me how many valence electrons there are. That tells me how many dots I need to put on the symbol. This version of Hund's rule tells me how I'm supposed to separate those dots from each other. So I keep them all separated until I have 4, and then I start doubling them up. Order doesn't matter. So what order I put these in, top versus bottom, left versus right, bottom versus left, doesn't matter. Put them in whatever order, whatever way makes the most sense to you. So let's take a look at some examples. So for lithium, I look at the periodic table. I see that lithium is in group 1. So lithium is going to have 1 valence electron. My Lewis dot symbol for lithium would just be its atomic symbol, Li, and then 1 single solitary dot. Where does that single solitary dot go? Doesn't matter. Left, right, up or down, doesn't matter. For aluminum, find aluminum on the periodic table. Okay, it's in group 13, also known as group 3A. Number of valence electrons is the same. If I have a double-digit number, I take away 10. So 13 becomes 3. There are 3 valence electrons for aluminum. Where do they go? Doesn't matter, so long as they are separate. So it's not going to be 2 and then 1. We gotta follow Hund's rule. Gotta separate all 3 of them from each other. Again, exact location does not matter. If you want to leave that blank one on the bottom, fine. Want to leave it on the top, fine. Want to leave it on either side, perfectly okay. When we get to molecule drawing, there are going to be some places where it makes more sense than others. But for right now, doesn't matter. Oxygen. Oxygen is O. O, group 16, 6 valence electrons. So I need 6 dots. Where did the 6 dots go? Doesn't matter. I just have to separate them before I start pairing. So 1 here, 1 here, 1 here, 1 here. That gives me 4. Now I can double up 5 and 6. Again, where the double dots are doesn't matter so much. What matters ultimately here is that my Lewis symbol for oxygen has 2 sets of pairs and 2 sets of single dots. Finally, for fluorine, symbol is F. Fluorine is a halogen, group 17, so 7 valence electrons. Where do they go? Again, doesn't matter. I just need to separate them. 1, 2, 3, 4, 5, 6, 7. Location and orientation don't matter so much. What matters is that I have 3 sets of pairs and 1 unpaired dot. That is the correct symbol for fluorine. Whether that single dot is top, bottom, left, or right, really doesn't matter. All right, questions so far? Okay, so let's talk some principles of bonding then. Now, our general octet rule says that atoms are going to bond until they get to 8 electrons. Now, how they get to 8 varies. They can add electrons to get to 8. They can drop electrons to get to 8, or they can share electrons to get to 8. Now, which path they choose ultimately kind of depends upon how many dots they have in the first place. So there are some general trends that we can follow. If I'm dealing with metals and non-metals, we tend to see adding and subtracting taking place rather than sharing. And that should make some sense to you, right? If I'm lithium, I've got the 1 valence electron. Well, I only have 1 electron to share. So sharing that 1 electron takes me from 1 electron to 2 electrons. That really doesn't do a whole lot for me. Still pretty far away from 8. I could add 7 electrons to get me to 8. That would seem like it's a lot of work to do. The easiest path to an octet for lithium is to drop that 1 electron that it has and settle into the noble gas configuration of its core. And that's what metals usually do. That's why they drop electrons. That's why they form positive ions instead of negative ions. It's a lot easier for them to drop 1 electron, drop 2 electrons, drop 3 electrons, than to try to add 5, 6, 7 more. The only time we really see covalent bonding, electron sharing, is when non-metals are coming together. And the reason it works primarily is that with non-metals, we already see that they have a number of valence electrons. Sharing comes from pairing up the unpaired electrons that they already have. So let's talk about ionic bonding first, probably because it's the easiest to at least see visually at this point. In ionic bonding, we see that the metals give up their electrons and the non-metals take electrons. And as a result of this give and take, we end up with positive ions and negative ions. So take, for example, and we have lithium and we have oxygen. If lithium ditches this electron and becomes lithium plus, it now has an octet based upon its core electrons. It now has a noble gas configuration of helium. Oxygen, on the other hand, the since it has 6 valence electrons, it's gonna have to grab 2 more electrons to get to 8. Those extra 2 electrons will give it a -2 charge. And so in addition to the 6 electrons it already had, those 2 extra electrons help it fill its octet. Now it's got 8 electrons around. This is the reasoning behind those periodic trends that we discussed when we started talking about nomenclature and trying to predict charges. This is how we could say, oh yeah, the alkali metals, they're all +1 in charge. The halogens, they're all -1 in charge. The nitrogen group, they're all -3. How did we come up with those? The octet rule was the main thrust behind those. It's for that same reason, thinking about a charge balance standpoint. If lithium and oxygen were going to make a compound, what compound would they make? What would its formula be? Yeah, I would need 2 lithiums and 1 oxygen. Why those 2? Well, if we want to get real technical about it, these electrons that are coming into oxygen came from the lithium. And so if I only have 1 lithium, that's only 1 electron. That puts me 1 short on the oxygen. So I need a second lithium there to give me the second electron to fill up oxygen's octet. Now, from a charge standpoint, at the time we talked about charge balance. The fact that the charges aren't balanced means that we have to balance them. That's when we did that crisscrossing thing to figure out the subscripts. Now we can start to see that's why we can do the crisscrossing thing. That crisscrossing thing helps us to figure out how many of each ion I need to balance out the number of electrons that are moving. And so if we put that into kind of the proper perspective, these electrons from lithium are the ones that are being taken by the oxygen. And that's how we come up with the chemical formula Li2O for this ionic compound. Because in order to get oxygen to its octet, I need 2 lithiums giving up their electrons. So Lewis structures like these can help us to see from the molecular standpoint, why what we kind of took for granted as knowledge a couple of chapters ago, why that ultimately makes sense. Why do we get the charges that we get? Well, the octet rule tells us this is how many electrons we need. Why does my ionic compound come out this way? Well, to get the octets that I need this many of each atom to give me the electrons to make it possible. Questions with this? All right, let's move off of ionic bonding. Let's talk covalent. Now, the key trick to covalent bonding is that we have to get it away from the idea that the electrons are being exchanged, that they're leaving in company. What we need to think about instead is that those electrons are being shared. And so what we want to look for in the Lewis structures of covalent compounds are those unpaired dots, because the unpaired dots are the ones that need to be paired up to get into the octet. If I already have them paired up, that little orbital is already full, because only 2 electrons fit in any one orbital. So what I need to think about is sharing. How do I get my atoms to share electrons to get me to that 8 valence electrons? And in particular, where are there opportunities for sharing? Where do I have unpaired electrons available that I can link together to create that bond that allows those 2 electrons to be shared between the 2 atoms? Couple of important pieces here. First of all, shared electrons are counted by both atoms. So if I've got one atom sharing an electron with another atom sharing an electron, those 2 electrons that are shared now belong to both atoms and get counted as part of both sets of octets. The other thing that we want to think about is with covalent bonding, there is a concept of multiple bonds, where it's possible not only to just share 1 electron in each direction, 2 in total, but multiple times. So when 2 electrons are shared in total, we call that a single bond. When 4 electrons are shared, 2 from each atom, we call that a double bond. When 6 electrons are shared, 3 from each atom, we call that a triple bond. As you might expect, as each new bond gets added, the strength of the interaction between the 2 atoms increases. The more electrons they share, the more attracted to each other they become, the stronger that bond between them is. Another really important trend here. When we're talking about covalent bonding, generally speaking, at least for our purposes here, we want to look at the number of unpaired electrons for that atom. That tells us how many bonds it can and will make. And this is where we are going to depart from the way that the book talks about covalent bonding and Lewis dot structures. In the book, they're going to get into some ways of drawing that more closely align to how I would teach it to a Chem 105 class. And we're going to step away from this. We're going to talk about things from a more simplistic standpoint. These are general rules that kind of govern probably 75–80% of molecules that you would encounter. We'll cover those fringes in Chem 105. So don't worry about those at this particular time. It's also why I didn't assign that particular section out of the textbook as part of the readings, because it gets way too deep into the weeds way too quickly. So from this simplistic standpoint, when we're starting to figure out how things bond, what we want to look at is how many bonds can something make, and trying to make a molecule that kind of makes the most sense based upon a couple of key ideas. And so when we go from talking about atoms and their individual electrons to a molecule, we go from Lewis dot symbols to something called a Lewis structure. The Lewis structure gives us an idea of how that molecule is put together in terms of its bond. And so that's the main point of this exercise that we're getting into here in chapter 10. How can I put these molecules together? How can I put these atoms together to give me a molecule overall? How are they bonded together? What kinds of combinations of bonds exist in this molecule? To answer that question, we're going to have to follow a process. And the process here is relatively simple. There are two steps in this process. The first step is I need to figure out what atom is going in the middle of my molecule. We call that the center atom. Now, from our standpoint, the center atom is going to be the one with the greatest bonding potential. That is the one that has the most unpaired electrons. So from that standpoint, the carbon group is probably the best as a center atom. Carbon group has 4 valence electrons. We know that all 4 of those electrons are going to be unpaired because of the way that Lewis symbols work, as we separate all the dots from each other. So I've got 4 dots all unpaired. That's 4 potential bonds for carbon. Next on that list would be the nitrogen group. The nitrogen group has 3 unpaired dots. Then the oxygen group with 2, then the halogens with just the 1. So that's the first task. The first task is we got to figure out what goes in the middle. And for that, we just look at the Lewis symbols and we say, okay, this one's got more unpaired dots. That's the one that's in the middle. From there, we try to connect everything else to that center atom by simply pairing up the unpaired dots with each other. If we can do that, chances are pretty good that by the end of the process, we'll have done two things. We'll have gotten everybody an octet, and we will have paired up everybody's unpaired electrons. And that's as much as we can ask for anything. We want all atoms to obey the octet rule. We want all the unpaired electrons to get paired up. And so that's all that we try to do. That's all that we can do. Let's take a look at some example problems. So for carbon dioxide, I have carbon. So carbon's Lewis dot symbol, 4 valence electrons, all 4 of them separated out. For oxygen, oxygen has 6 valence electrons, so its symbol looks like this, which means I've got 2 unpaired dots. So my first task is between these 2 atoms, which one should go in the middle? Which one has more unpaired dots? Carbon. Carbon has 4 unpaired dots. Oxygen has 6 dots in total, but only 2 of them are unpaired. 4 of them are paired. So my carbon needs to go in the middle. And so what I'm going to do to make this easier on myself, I've got 2 oxygens to put around it. I'm going to put 1 oxygen on either side. Now again, the exact placement of these dots doesn't matter that much. But what you'll find is that when you go to pair them up with each other, there are going to be some places where it's easier to pair them up than others. So for pairing purposes, I just want to pair up the dots that are unpaired. It's like that. So there are lots of places where it would have made sense to have those unpaired dots. If you had drawn your unpaired dots on the outside extremes, it would have been just a little bit harder to pair them up because you would have to go all the way around the symbol itself to get them to pair up. Last thing that we want to do is we want to redraw this using lines to symbolize the electrons that we paired up, just to make it look a little bit neater. So when I do that, I'll have carbon in the middle. I'll have 2 lines to the oxygen to represent these 2 bonds. And the oxygen will still have 4 unpaired dots around it. And the same thing on the other side. So this is my Lewis structure with carbon dioxide. Carbon dioxide features a carbon in the middle and 2 sets of double bonds to the oxygens on either side. From an octet rule standpoint, I look at carbon, where each one of these lines represents the 2 electrons that are being shared. So I've got 2, 4, 6, 8 electrons around that carbon. And for each of the oxygens, I've got 2, 4 from the bonds, 6, 8 from the ones that were paired up on the oxygen already. So carbon meets the octet rule. Oxygen meets the octet rule. Everybody meets the octet rule. And all of our unpaired electrons are now paired up. That's exactly what we want out of one of these Lewis structures. We want to hit all of those criteria. All right, let's look at another example. With methylene chloride, I have carbon. So the Lewis symbol for carbon is this. I have hydrogen, which hydrogen is in group 1, so it just has the 1 dot. And I have chlorine, which is a halogen. It's got 7. So it looks something like that. So those are the 3 atoms I have. Which one of those would make the best center atom? Which one has the most unpaired dots? Okay, it's carbon again. Carbon has 4 unpaired dots. The hydrogen just has 1. The chlorine just has 1. So when I go to draw this, I'm going to put carbon in the middle. And then I'm just going to surround it with, I have 2 hydrogens and 2 chlorines. And now all I want to do is just pair up unpaired dots. So this hydrogen dot's going to pair up with another dot. This hydrogen dot's going to pair up with another dot there. This chlorine dot's going to pair up with one of these carbon dots. This chlorine dot's going to pair up with one of these carbon dots. Every unpaired dot has been paired up with something. Only thing I want to do now is just redraw it to kind of clean it up a little bit so it looks a little bit less funky. So carbon in the middle, single bond to each of those hydrogens, single bond to this chlorine. This chlorine still has 6 dots around it. Single bond to this chlorine. This chlorine still has 6 dots around it. So I've paired up all of my dots. Am I meeting the octet rule? Well, for the carbon, I've got 4 bonds, 2, 4, 6, 8 electrons in total. So its octet's fine. For the chlorine, I've got 6 dots plus this bond. 6 plus 2 is 8. So the chlorines are okay as well. For the hydrogen, I have the 2 electrons in the bond and no dots. Is that okay? The answer here is yes. Why is it okay? Why does hydrogen not have to obey the octet rule? Well, look at its noble gas. How many electrons are in helium? just the two. So for hydrogen and helium, and for any ions that take on helium's configuration, we use a variant of the octet rule called the duet rule. And it basically just means that you only need 2 electrons to fill out that first energy level. And so if the first energy level is your only energy level, 2 is enough. So for hydrogen, I only need to make the 1 bond. It's okay. Speaking of hydrogen, we look at this last example. I've got 2 hydrogens, so each of them would have just the 1 dot. All I would need to do is pair them up. And if I redraw that, I just need to show that bond between them to signify that they're sharing those 2 electrons. So sometimes your Lewis diagrams are really just that simple. They're just a matter of connecting whatever electrons are, unpaired between 2 atoms. In cases like methylene chloride, it looks a little bit more complex just because there are more atoms there, but it comes down to the same fundamentals. I need to pair up the electrons that are unpaired, starting from the center atom and working my way out. All right, get yourself a participation point. Since we are running out of time here, what I will do is I will answer this question and put it into the annotated slide deck in Blackboard. So if you go to the lecture prep area and you go to the slides for chapters 9 and 10, there are 2 slideshows there. One is the blank slides. One is the slides that have my notes, all the stuff that I've been writing down on them. So what I would encourage you to do, the post-lecture tonight is going to be this kind of stuff. Drawing out these simple structures and kind of working your way through that. It might not be a bad idea to just run through and do these just as practice before you get into that assignment. And so I'll post the answers to that in that annotated slide deck so that you can see it. Last chance for this participation point. Go ahead and get it in. And then on your way out, one last participation point for just your general feedback and how you're feeling about this particular lesson. So on Wednesday's our last day of the week. We're going to dive into chapter 13. Chapter 13 is all about solutions. And so what we're really going to focus on are the calculations around solutions, because we've already kind of talked about solutions as a concept. So bring your calculators and your periodic tables with you on Wednesday. We're going to need them both. Have a good afternoon.